Good evening. Welcome to the problem solving session for Basic Electronics course of NPTEL with code NOC23E62. This is the 11th week that we are discussing the problems for this course on today's April 15, 2023. My name is Amit. I am a PhD scholar at ISC Bangalore. And for the past 10 weeks, we have been solving some problems related to the course, related to the subject matter that has been uploaded to the NPTEL course website. So in the first session, we started with Thevenin-Norton equivalence and nodal analysis and superposition theorem for some basic circuits. And then we saw their transients, RCRL transients, and how does switching impact those transients. Then we switched to semiconductor physics, mainly firstly diode-based circuits like clamper and peak detector. And continuing with that, we also saw the half-wave detector, which was based on diodes. Then we switched on to DC biasing in BJT circuits. BJT is again bipolar junction transistor, again a semiconductor device. Then we saw some very common application of BJT, that is common emitter amplifier, and related to that, we saw the two small signal models. Note, this is the biasing was DC biasing. Here we talk about small signal analysis, that is AC signal analysis, and we saw the two common models, the hybrid pi model and the T model of BJT, and one more application in the form of a push-pull amplifier. Then we moved on to operational amplifiers, and we saw their basic operations, especially with the negative feedback circuit and the comparator circuit, and some applications of negative feedback circuits. Then we saw in the next session 7, we saw some non-idealities in op-amp circuits, like offset current and offset bias and related things, and CMRR and stuff like that. One more application we saw was difference amplifier, which is an application of op-amp. In session 8, one more application was precision amplifier, where we included diodes as feedback elements or some other circuit elements in op-amp circuits. Then we saw a very common application of op-amp, which is as a filter. So filter essentially it means it's a frequency response, that is you don't want to pass certain signals above or below a certain frequency. And that's how we saw in as op-amp as a filter, in which we saw something called transfer functions and Bode plots. So Bode plots, so transfer function essentially nothing but the gain of a circuit expressed in terms of frequencies. And Bode plots, there are two Bode plots, the magnitude Bode plots as well as the phase Bode plots, and we saw how their profile looks like depending on the transfer function. Finally, we saw some positive feedback for op-amp circuits in the form of Schmidt trigger and oscillator circuits. And then finally, in the last session 10, we had switched to digital electronics, in which we talked about combinatorial circuits, primarily Boolean algebra, logic gates, truth tables, and Karnaugh maps. And we saw that how these three approaches can be interchangeably used to arrive at a solution for a given problem. So we'll continue with that today, the digital electronics part. And just a second, we will continue with that. So as you saw, Boolean algebra, there are three primary operations: conjunction, disjunction, and negation. We had talked about in the last class. Conjunction is your AND gate, disjunction is your OR gate, and negation is your inverter. And there are two values which talk about low and high, or in this domain we talk in terms of zeros and ones. We also saw X, that is don't care. Here X means it can be 0 or 1, but we don't care about it. So it can be 0 or 1 depending on our usage. And these are the two very basic laws which we saw. These are called De Morgan's laws, where we can use, you can see this is to convert from an AND gate to an OR gate, right? And conversely, from an OR gate, this plus denotes OR gate and this dot denotes AND gate. So you can interchangeably use while solving the expressions, the Boolean expressions. And these are some of the very common logic gates. And so for instance, the frequently used ones are NAND, NOR, XOR, and OR, obviously. So these are the truth table. Truth table is nothing but a set of possible combinations of all the inputs. So you can see in this, let's say in XOR, right? So this is the XOR, this is the expression, and it's also written as A bar B plus AB bar, right? So there are two inputs, A and B, right? So we write all four combinations 0 0 0 1 1 0 1 1, and based on this algebraic expression we can obtain the value of X. X is the output over here. This is called a truth table, and we'll again revisit this in today's class. Okay, so till now whatever we had talked about in previous session and up until now, I've been talking about combinatorial circuits. So what do I mean by combinatorial circuits? If I had to represent them in a very simplistic model, it's this. So this is some black box, this is some circuit, I don't know what is inside, BJT, op-amp, whatever is inside, it's a black box, and I'm calling it a combinatorial logic circuit. So some inputs are coming, this means some voltages, some signals A, B, C are coming here, A, B and C, digital inputs, right? And they may, let's say there is an output X and an output Y, right? So X and Y is a function of A, B and C. Output is a function of just the A, B and C, not the previous values, just the current values. So the way to say is that output values depend only on present values of inputs. Okay, so just to illustrate what do I mean by that, consider this AND gate. So if A and B both are 1, the output is 1. If due to whatever reasons, let's say B remains 1 but A becomes 0, so this is case 1, this is case 2, right? Then output will become 0. Why? Because the present values are 1 and 0. It has no information about the past, it only looks at the present values. Whatever the present value, if the output is dependent only on the present values, that's a combinatorial circuit. That's what I am saying. Output values depend only on the present values of inputs. That's a combinatorial circuit. On the other hand, sequential circuit, you see this block is the same as previous one. So sequential circuit has some combinatorial logic circuit as well as some memory, right? So what is this? What do we mean by memory? This memory we implement it using different. So memory's function is to store some values. It will store some values. Okay, so output you can see is dependent on input. So these are the inputs A, B and C, as well as there is some data coming from memory, and when these two are combined you get an output. So so here I can write that for sequential circuit, output values depend on present. Why present values? Because this input, this is also going into this black box, present as well as stored values. Stored values are usually in memory, and there are examples of it like JK flip-flops, D flip-flops. We'll see in today's class what are some common memory elements. So, and usually memory and sequential circuit, a key thing to remember, sequential circuit, you more often than not you will see a clock or some storage. So if any circuit involves some of the flip-flops, JK flip-flop, D flip-flop, T flip-flop, T is for toggle, D is for delay, this means, and usually there is a clock involved. So these are some signs which you should look out for to determine whether it's a sequential circuit or a combinational circuit. Okay, so now we are equipped with what is a basic understanding of sequential circuit is. Now we'll look at some of the very basic circuits and problems related to them. Okay, so the first problem for today says that the S bar and R bar inputs are shown in the figure. So in this figure you can see the S bar and R bar inputs as a function of time are applied to a NAND latch. This is a NAND, this is called a latch. You can see these are the two NAND gates, NAND 1 and NAND 2, and we'll analyze a bit, but this is called a latch. Assuming them Q is 0 initially, so there is an output Q, you can see the Q here, and Q bar is nothing but inversion of this. Bar denotes inversion, as you know, which plots give the correct waveform for Q. So we are given this circuit and we are given the signal for these two inputs, S bar and R bar, and we are required to find the output. It's as straightforward as that, right? So let's just first have a look at this component. What is it? So it is also called an NAND latch or an SR latch. S stands for set, R stands for reset. Set and reset, and bar denotes the inversion. Okay, and this is the truth table for this particular circuit. So let's pause a bit here and let's try to analyze. So what's happening is that if S bar is 0 and R bar, okay, let's just try to take this one. This is the simplest to understand. When S bar is 1 and R is 1, okay, when S bar is 1 and R is 1, Qn plus 1, this means the next value of Q. So you see Q will keep on changing, as you see here. It's keep on changing with respect to time. So this means the next, whatever the next value of qn plus 1 will be the same as qn, and hence the action is no change. So if qn plus 1 is equal to qn, hence we are calling it a no change. On the other hand, if we set r bar equal to 0, this means r equal to 1, r bar equal to 0, that would mean r equal to 1, right? Reset equal to 1. So when we are resetting, the value of q should become 0. So let's try to see this, what's going to happen. Okay, let's put r bar is 0, r bar is 0, this, and s bar is 1, s bar is 1. Okay, let's see what happens. So what's going to happen is that, let's say this value is q. So what is going to be q bar? Q bar is simply the NAND of q and 0. So this is going to be 0 times q bar. 0 times something is 0, 0 bar. So q bar will become 1. If q bar becomes 1, then naturally this implies q equal to 0. And that's what we are seeing here. So r equal to 1 and obviously s equal to 0, that's also the case here, both of them, that will reset the output value. So q will become 0. All right, and similarly what we can see, let me delete these. Okay, well, let's just take one more case. So now take this case. So in this case, s equal to 1 and r equal to 0. This means we want to set the memory to 1. So q is essentially storing this value. Okay, s equal to 1, r equal to 0. So let's do this. S equal to 1, r equal to 0. Okay, s equal to 1, r equal to 0. Let me delete these values. Okay, s equal to 1, r equal to 0. Yeah, wait a second. Yeah, s equal to 1 and r equal to 0. So let's try to analyze that. So it will be again 0 times q whole bar, 0 bar. This means, sorry, r bar is 1 here. Sorry, my mistake. Yeah, so s bar is 0 and r bar is 1. So this value is nothing but q bar. Let's try to find the value of q. Q will be nothing but 0 times q bar. This is a NAND gate, whole bar. 0 times something is 0. That will be 0 bar, it will be 1. So q will be 1. That's what we are seeing here. This means the value that will be stored in the memory in this NAND latch, whatever it's storing. A latch means something to grab, to hold in English. So that's why this is also called a latch. So it will remain to be 1. However, in the third case, when both are 1, when both are 1, and that's also a case, I'm not going to derive that here, but the idea is that, as I told you, truth table, you list all the possible combinations of input and you can obtain the output, and that's what we are doing. So I showed you 2 cases, rest you can see for yourself. All right, so now this is the values of inputs that is given to us, and we also know this is the truth table. All right, so now I'll simply draw the output as a function of time. This is the output q. Okay, so let's now divide it into certain chunks here, because then only we'll be able to apply the truth table. Okay, so I'm just highlighting all the transitions that are happening. So each and every transition, we'll see after each and every transition what will there be any change in the value of output q, and if there is a change, what is that change? Okay, now let's look at the first period. I'm going to use a different color, purple color. So let's look at this first period, this period first, from here to here. Okay, so s bar is 1, r bar is 1, s bar is 1, r bar is 1. It says no change. So whatever is the value of qn plus 1 will remain qn, and originally it was given that before time equal to 0 it was 0. So this means in the first period there will be no change as compared to the previous period. This means it will continue to be 0. Now let's look at the second period, this period. In this period, s bar is 0, r bar is 1. So s bar is 0, r bar is 1. This means the value of q should become 1. So this means in this period, in second period, the value should become 1. Okay, let's see the third period now. Third period is from here to here, In the third period, we see S bar is 1 and R bar is 1. S bar is 1, R bar is 1. Again, no change. So in the third period, whatever values was in the second period, it will remain the same. Second period was high. Third period again, it will remain high. Now this is the fourth period. Fourth period, S bar is 1, R bar is 0. S bar is 1, R bar is 0. That's a reset condition. So Q should become 0. Q will become 0. This here, this is the fifth period. Both are high. Again, no change. So no change. This is the sixth period. From here to here. This one. This one you can say. Sixth period. S bar is 1, R bar is 0. S bar is 1, R bar is 0. It's a reset condition. So Q should become 0. So Q will become 0. It's already 0. So it will appear as if no change. Again in this period, the seventh period, both are high. No change. It will remain like this. In the eighth period, S bar is 0. So this is the eighth period. This period. In the eighth period, S bar is 0, R bar is 1. S bar is 0, R bar is 1. Q value will become 1. Q value will become from 0 to 1. It will continue to be this, and then in the ninth period, both are high. Again, no change, so it will continue to be like this. And then for this 10th period, S bar is 1, R bar is 0. S bar is 1, R bar is 0. So it will become to be 0 like this. And then again in the next, both are high means no change. So it will continue to be like this. So this is the waveform that we have obtained. So we'll try to see that which of the outputs match this waveform. Okay. So let's go to the next slide. So we see it becomes high after the second interval. So this cannot be the answer. You see there's one period and two, so only two highs. Again, this cannot be. This is also not the answer because this period is very small here, you see. So the correct answer would be B. This and then this. Let me check. Yeah, B is the correct answer. So that's what we have determined here. Okay, so just to summarize that we saw this is the SR NAND latch, set reset NAND latch, and this is the corresponding truth table for that. So we divided our inputs, the S bar and R bar input that were given to us, into different time periods, and then for each time period we found out the value of Qn plus 1, that is what will be the value in the next time period. It will also note Qn plus 1 depends on the present values of S and R as well as on some previous values, right? Because when there is no change, so you see in this part it was no change, right? If no change means what are the previous values. So if previously was 0, it was 0 again. Here it was again no change, but since previous was 1, next was also 1. That's what I mean, that the present value will depend not only on the value of the inputs S and R, but also on the previous values, which is in this case Qn. So we applied this logic and we saw that so this is the waveform that we obtained, which happened to be option B. Okay, so this is one of the very simplest sequential circuits, NAND latch. Okay, another type of memory device is a JK flip-flop, and this problem is based on that. Okay, so the question says the clock J and K waveforms for a positive edge triggered JK flip-flop are shown in the figure. So these are the figures you can see. So clock J and K is shown in each of the figures. The flip-flop output Q is 0 initially. So initially it's 0. Which option correctly describes the Q waveform? So we are given the clock J and K, and we are required to find how does the output waveform look like. And initial value of Q is 0, which you can see in all these four waveforms. What this means is that at this part it's 0. That's what we saw in the last question also for NAND latch. Okay, so again we'll proceed in the similar manner as we did before, but first we need to see what is a JK flip-flop. Okay, so on your screens you can see the JK flip-flop. So this is the symbol for that. So you see two inputs J and K and a clock, and you see two outputs Q and Q bar. Q bar is nothing but just the inversion of whatever the output Q here is. And this you see clock is coming input, and you see this edge. So this symbol denotes edge triggered. Means whatever the changes in Qn plus 1 are coming, this means the future state of Q will only happen at the edge of a clock. So clock is coming like this. Right? So at J and K are changing like I don't know, whatever, it doesn't matter. So So like this. So we will only, so this is the positive edge and this is the negative edge. We are interested only in positive edge. This symbol denotes a positive edge. So you can see that whatever the value of j and k, only that will be taken, not anybody else, while applying this truth table. Okay, so now one more thing, as you can clearly see, this truth table is very similar to what we saw of the previous SR latch. Okay, so there also it was 0 1 was 0, so you can say that this is the reset condition. So this is like an S, this is like R, set reset, and 1 0. So when you want to set it to 1, so Qn plus 1 will become 1, and we saw that their S bar R bar when both were 1, right, it was no change. So here again this is no change condition, this is no change, this is reset, this is set, and this is what is known as toggle. This was forbidden, this state was forbidden for SR latch or NAND latch rather, right? But here if both the inputs are 1, the output, the new output will be the inversion of the previous output. That means if previous output was 0, the new output would be 1. If the previous output was 1, the new output would be 0, and hence this state is also known as toggle state. This is set, this is reset, and this is, as you can see, no change, because the next state will be same as the previous state. Alright, and I told you this denotes an edge triggered, and to be more specific, this denotes positive edge triggered, which we are required to see in this problem, and you can see that's how I denoted the positive edge, because this is the rising edge from 0 to 1. This is called the positive edge. On the other hand, if I want to denote the negative edge, which I am denoting in purple here, this is the negative edge. Negative edge, so this is the negative edge, right? Now, and this is the symbol for positive edge. Now, next question naturally arises, how is the negative edge triggered symbol look like? So, negative edge triggered symbol looks something like this. The truth table remains the same. This is Q, this will be Q bar. This is the input J, this is K, and you will denote a circle here. A circle means inverter. This denotes a negative edge triggered flip flop. We'll see one more problem, we'll see 1 or 2 problems related to negative edge triggered, but that's how the symbol looks like. The only difference is that now all the transitions will happen at the negative edge instead of the positive edge. But in this problem, we'll consider only the positive edge triggered flip flop, JK flip flop. Alright, so that's the truth table that we have come to know of the positive edge triggered. This again, you see this positive edge upward symbol, this is positive edge triggered, right? And we were given that these are the waveforms. These are given in the problem itself. So now I'm just required to find the value of Q. Okay, so let's do that. Let me first, okay, so this is a positive edge triggered, so let me draw only the positive edges. I'll highlight only the positive edges like this. These are the positive edges, and you can also see the dashed lines that are the corresponding to those positive edges. So let's extend those reference lines to our output waveform, so that it becomes much more clearer as to what we want to draw. Alright, so that is complete now. Now I'll simply I'll choose a different color. Yeah, so now I'll just, again, as we did in the previous time, so we'll see again, or note that the original value was 0, that is given in the problem itself. If you remember, somewhere it was written, yeah, Q is 0 initially. So initially Q is 0, that means for t less than 0, Q is 0, which is denoted by this. Okay, so now at this positive edge, J is 0 and K is 0, right? J is 0 and K is 0. So J0, K0, Qn plus 1 will be Qn. This means this stage will be the same as previous stage. Previous stage was 0, so this will also be 0. Okay, now let's look at this positive edge. We don't care what's happening in between, you only look at this edge now. At this edge, J equal to 1 and K equal to 0. So I'll write here actually 0 comma 0, right? Here it's 1 comma 0. 1 is J, K is 0. So 1 comma 0, Q should become 1. So Q will become 1 and will remain 1 until here. At this positive edge, it's 1 1. J is 1, K is 1. So 1 1 denotes to toggle. This is the toggle stage. Toggle means whatever is the stage, you invert that. So it's high, then it will become low. So it becomes low. It will remain low up until here. At this edge now, at this edge it is 0 comma 1. 0 and 1, 0 and 1, 0 and 1. This means it will reset. JK flip-flop will reset to 0. This means 0 remains 0. And now at this edge it's 0 0 0 0. Here also it was 0 0. At 0 0, what's the stage? The next state should be the same as previous state. So the next state, what's the previous state? Previous state is 0. Next state will also remain 0. Now here it's 1 1. Now 1 1 means toggle Q and bar. So next state will be the toggle of previous state. So this will toggle. Previous state is 0. So new state will be 1. No, toggle was here also, but here since the previous state was 1, next state will be 0. Toggle here again, but previous state is 0, next state is 1. That's what I mean. A sequential circuit, it's not only depending on the value of J and K. J and K are both 1 here, but the output stage is 0 and 1 here. Okay, and the next positive edge, it's 0 0. Sorry, it's here. So it's 1 1 again. 1 1. 1 1, we know again toggle, so it will toggle from 1 to 0. Next is 0 0. Value 0 0. 0 0 means no change. So it was 0 here. So next clock cycle will also remain 0. And again on this edge, again 0 0. 0 0 again means no change, as you can see the first line of the truth table. So no change means initially 0, finally also it will remain 0. So this is the waveform that we have obtained for the output of this JK flip-flop for these given inputs and clock cycle. So this is the waveform. Now let's see where it's high. So it's high in this second period and 3 4 5 6th period. So it's high in second and sixth period, otherwise it's 0. So let's try to plot this. Let's try to match the waveform. So it's high in second and sixth. Okay, let's see, it's high in second, 3 4 5 and 6th. So yeah, A is the answer. Let's check the other. Second and third, so this can't be. This is second, but 6 and 7 this cannot be. This is again 3 of them. So A is the correct option. So in this problem what we saw again a sequential circuit which involves a JK flip-flop, and we saw this is the truth table for a JK flip-flop. This denotes a positive edge triggered, as that means the J and K values will only matter only at the positive edge of the clock. So this is the clock, and this is the, I have highlighted the rising edge or the positive edge, and we saw whatever the values of J and K are there, and we applied the truth table on that, and we saw all the 4 conditions: no change, set, reset and toggle. So and we obtained this the waveform, which happens to be option A in this case. Okay, so till now we have seen 2 problems related to 2 very basic the devices for sequential circuits. Okay, now let's go ahead. If there are any doubts, you can ask at any point of time. If for that matter, you can stop me at any time, and I'll respond to the queries if any. Okay, let's go ahead. So this question asks, what is the minimum number of flip-flops required for a mod 40 counter? So there are 2 or 3 key terms here. What's a mod 40? What's a counter? Flip-flop we saw. So flip-flops is nothing but these devices that we are seeing. Why are they flip-flops? Because they change the value from 0 and 1, and they also store. So those are flip-flops, and the other key term here is minimum. Right, so let's first talk about this term counter. So counter is anything that counts. Okay, so for instance, in primary classes we learn, or even earlier in some cases in pre-primary, we learn to count. So we count, let's say, from 0 1 2 3 4 10. This is very basic, 0 to 10. So this is a counter. So any device which outputs first 0, then 1, then 2, then 3, then 4, then 10, it's a counter, right? Since it's counting up, this is also known as a up counter. On the other hand, there's a down counter also. Down counter will start from, let's say, it's only single digits. For it can be anything. So 9, 8, 7, and it will go down to 0. This is a down counter. It starts from 9 and it goes down, right? So what's happening is that, so this is a counter. Okay. Now second term here is mod 40. So let's understand what does mod n counter mean. Counter we have seen, what does mod n mean? So here n denotes the number of states, rather not the number of states, I should not say number of states, it's the maximum value that can be reached, maximum decibel value. It's the maximum decimal value to be counted. Okay, what does mod denote? So mod usually means let's first understand the term n. Okay, for instance, if I have a mod let's say 10 counter, okay, so mod 10 counter, this is maximum decimal, sorry, -1. Mod 10 counter will count from 0, 1, 2 to 9. Similarly, mod 20 counter will count from 0, 1, 2 to 19. You will now understand what does this mod mean. Mod stands for modulo or modulus, or in other words, remainder, to be put in very crude terms. So for instance, you are given any number. So let's say you are given 39. You take a remainder with 10. What will you get? 9. Maximum remainder that you can get is the divisor -1. Hence this maximum decimal value. Hence this term comes. So modulo n means you will count from 0 to maximum decimal value -1. Okay. So I should say it rather like this. This is the same thing as what we are doing. So maximum decimal value, what will it be? It will be n-1. So you can see that max value will be n-1. So this is what we have to keep in mind. So for mod 10 counter, it will be 9. Okay. So for mod 10, it will be from 0 to 9. Similarly, we are interested in mod 40. So we are required to count from 0 to 39. Mind you, these are all decimal values. Okay. But all the flip-flops that are storing, these are storing in binary terms. So 0, 1, that's it. And one flip-flop, so this means, so 39 requires how many bits? That's the question now. Okay, so we know that to store 31 is 2 to the power 5 minus 1. So this means to store 31 we require 5 bits. Similarly, to store 63, that is 2 to the power 6 minus 1, you require 6 bits. It's 2 to the power n minus 1. That's the same thing that's happening here. So 2 to the power 6 is 2 to the power 3. That's 8. 8 into 8, 64. Yeah, this is correct. So to store up to 63 decimal value, you need 6 bits. So we need to store 39, right? That's what we need. We need to store 39, and that we cannot store for 5 bits. Okay. So this means that we need 6 bits. So what I mean to say is that we need 6 bits to count to 39, or other ways you can do, you can obtain the binary equivalent of 39. That's also a way, but it's a good, because when the numbers become very large, it's a good practice to count in terms of 2 to the power n minus 1. That's what I did. So we require 6 bits, right? And we also know that one flip-flop equal to 1 bit, right? This means we require 6 flip-flops. Simple unitary method. 39 requires 6 bits. One flip-flop is 1 bit. That means to count to 39 you need 6 flip-flops. Let's try to understand it a bit. So this is my first flip-flop. Again, you see this is a JK flip-flop, positive S trigger. This is the symbol we saw. So this will count. So this is the output Q, right? So this alone, right? This alone can count from 0 and 1, correct? Because output can Q, let's call them J0, okay, and Q0, 0th flip-flop can only count to 0 to 1, right? Now let's say you have 2 flip-flops. Okay, so what's going to happen? This is J1, K1, Q1, Q1. These two combined now can go from 0, 0, 0, 1, 1, 0 and 1, 1. That is from decimal 0 to 3. Correct? Let's add one more. Let's add this more. So let's name this again J2, K2, Q2 and all that. So these three combined, right, can go from 0, 0, 0 up to 1, 1, 1, which means from 0 to 7. Correct? That's how it's counted from. I'm just directly converting from decimal to binary, right? And similarly, finally, if you keep on going, let's say this is the 6th flip-flop, by 6th from 0 to 5. Okay, these are 6. So it went from 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1. This means from 0 to 63. That's the range we will cover, and we only require up to 39. So we'll be fine with these 6 flip-flops. I've not shown the middle two, but there are 2 more, J3 and this is 5. All right. So that's how that's what we mean, that you require to count to 39, because it's a mod 40 counter. You can we go up to 39. To go to 39, you require 6 bits to express in binary, and 1 bit is 1 flip-flop. Hence, you require 6 flip-flops. Okay. What happens if I add 7? If you add 7, you can go up to 127, right? So let's discuss this here. And now I'm going to emphasize the term, this term minimum, right? So 1 flip-flop, you can go from 0 to 1. 2 flip-flops, you can go from 0 to 3. Similarly, for 6 flip-flops, we saw you can go to 0 to 63. For 7, you can go to 127. So but we require only up to go to 39, right? So this setting, 7 flip-flop, will also take you to 39, but you are wasting resources, because that work can be done even in 6 flip-flops. 7 flip-flop will be useless in that case. Hence this term minimum. 5 flip-flops cannot work, because 5 flip-flops will only go to 31, and you want to go to 39. 39 is the number that we want to reach. This is our target. This cannot fulfill, this cannot fulfill. Similarly, this cannot fulfill. The least number of flip-flops is 6. 7 will also work. Hence the term minimum. So minimum is 6. Option C. If the question asked the number of flip-flops required for a mod 40 counter, and this was a multiple choice question, right, then the correct answer would be 6 and 7, because 7 will also work. So keep that in mind. The type of problems often come in your competitive exams, multiple choice question, gate and whatnot. So be careful about that. Okay. So in this we saw what do we mean by a mod 40 counter. Mod 40 nothing but modulo. This means you take the maximum remainder that remains when you divide by 40. That is 39. Hence our target was 39. And we saw 39 requires 6 bits to store in binary. This means we require 6 flip-flops. Minimum 6 flip-flops rather. And this is what the question was asking. So question 3 is answer C. Right. So till now what we have seen is various two or three memory devices and some very basic fundamentals of them. Now what we'll try to do, we'll try to use our knowledge to drive the circuits. Okay, and this is one such circuit. So in this problem it says that, so Q3, Q1, Q2, so these are 4 flip-flops. Okay, this is flip-flop 3, this is flip-flop 2, this is flip-flop 1, and this is flip-flop 0. There are 4 flip-flops and their output are Q3, Q2, Q1 and Q0, which is initially 1100. In sequential circuits you will very often see this thing. Initially the value is this. Now it says what is the state of counter shown in the figure after 5 clock pulses. Again this term counter comes. So why is it counter? Because if you express Q3, Q2, Q1, Q0, note each one corresponds to 1 bit. If you express in decimal, it will give you some number, right, between 0 to 15. And the way it's changing, it will be counting up, lower, skipping some values. We don't know what's going to happen, but that's how it's often referred to as counter. Okay, and you can also see a clock here. So we are required to find 1100 initially. What is the state after 5 clock pulses? This is the clock, and these are the D flip-flops, and this is a NAND gate that you can see. So, but first we need to understand what this D or delay flip-flop is. So this is a circuit diagram of a D flip-flop. You see one input D, and these are the outputs Q and Q bar. Q bar is again the negation of Q, and there is a clock input coming. So when the clock is 0, right, there is no change in state, whether the D is 0 or 1. It doesn't matter. The output will not change. The next state, right, so you see this is Qn plus 1, which was talking about. This is Qn. This is Qn plus 1. Qn. So when the clock is 0, when the clock is low, whatever the input, it doesn't matter, the output, the state will not change. However, if the clock is high, this means now this circuit will respond to the value of D. D stands for delay. Okay, this means whatever the input, after only one clock cycle, it can go to output. So if the clock is high, that means whatever the input, it can be passed to the output. If the input is 0, the output will be 0, and which is often referred to as reset, as we saw in other earlier cases. The clock is 1, this means the circuit is active, Zener circuit. If the output is 1, D is 1, the Q will also be 1. Okay, so this is a very simple circuit. So whatever the input, it will be passed on to the output provided the clock is high. That's a delay flip-flop is. Okay, so this is a circuit that has been given to us. These are the 4 flip-flops as we saw earlier, right? And essentially we are required to populate this truth table. So we are required to find, we are seen after the 5th clock cycle. So we are interested what's the magic, what's the state after this. Initially we know it's 1100, 1100. We don't care what these values are, okay, because this is the initial state that has been given to us. Okay, so what we are interested in finding out the final Q states, right? For instance, after 1 clock pulse, how it looks, second, third. But to find out Q, you see, this is the input side, this is the output side. We need the values of D, right? So we know this is the truncated version of the previous truth table. So here clock is 0 in this part, here clock is 1. So we'll only be considered about the lower part, okay, because we are assuming that the clock pulse means whenever the clock is high. Okay, so this is the first time clock will go high, second time clock will go high, third time clock will go high. So only the bottom 2 rows will be of relevance to us. Okay, so we know that Q value we can obtain based on the values of D. But how do we obtain the values of D? The question is silent about it. But you see this circuitry, right? What's the value of, let's start from here. What's the value of D0? D0 next state is nothing but what are the value of Q is? Q1. That's why denoting here. So D0 for first clock pulse will be nothing but Q1 of previous clock pulse. Correct? D0 of next clock pulse, this means D0 for here will be nothing but Q1 of previous. So Q1 of previous, it was 0. I write 0 here. So I'm populating this to be here. Okay. Similarly, D1, you see this wire. D1 in the next clock cycle is nothing but Q2 of previously. This is the wire. Okay. So D1 is nothing but Q2. This Q2 is 1. So this will be 1 here. So I'm populating this to be here. Correct? So D0 is nothing but Q1. So I'm bringing this here. I'm bringing this here. Okay. And finally D2 is nothing but whatever the Q3 is. Okay. So whatever the Q3 is, I'll bring it here. So that would be again 1. Alright. And finally, what is D3? D3 you can see is nothing but the NAND operation for Q0 and Q1. Q1 and Q0, you take a NAND of them. Okay. So Q1 and Q0, so this means 0 times 0. 0 times 0 whole bar, which is 0 bar, which is 1. So you see D3, D2, D1 and D0 just before the first clock pulse are these. What happens when the clock pulse comes? Whatever these values are, this will be passed on to the next one. Okay, that's where at the clock pulse comes. So this is just before the clock pulse, the input side. Okay, what is the output value of Q? Q will be nothing but whatever the value of D is. So output will simply be 1, 1, 1, 0. What will happen? Again, this logic will apply. So this will be passed on to the next input. So next input will become sorry. Again, we'll try to populate the next input. Again, D0 will be nothing but Q1. So this will be replicated here. Q2 will shift here. So this will be 1. And Q3 will be in D2. So this will be 1. You see these three are coming back here again. And this is nothing but NAND of Q0 and Q1. So this will be 1 times 0 whole bar, which is 0 bar, which is 1. Okay, 1, 1, 1, 1. What will happen when the clock comes? This truth table will get activated and we'll get 1, 1, 1 and 1. Right? What's going to happen? Again, these three will be populated because of these three. And this will become 1.1 whole bar, which is 1 bar, which is 0. this will become 0, and then when the clock comes, these three will get passed on, 0 1 1 1. So this is so what's, I'll denote with a different color. So here the transaction is linear due to the truth table. Okay, all the 4s are getting transformed, right? So, and now let's just keep on populating like this. So again, what will be d naught? D naught will be nothing but q1. So what's the q1? Q1 was 1. Again, what will be d1? D1 is nothing but q2. Q2 was 1. D2 was nothing but q3. Q3 was 0. So this will become 0. And this was q1 times q0. Q1 times q0, 1.1 whole bar, that is 1 bar, that is 0. Again, what will happen? These will get passed, so it will become 0 0 1 1, right? Again, these values will populate over here. This will come here, this will come here, this will come here, and this will be again 1.1 whole bar, which is 1 bar, which is 0. This will again get passed on when the clock comes, so 0 0 0 1. So that's the value we get, 0 0 0 and 1 add after the 5th clock pulse. So you can see that we can continue with this, right? So the next will become 0 0 0. This will become 0.1, which is 0 bar, this will become 1. So this will become 1 0 0 0, and you can see that you can continue this cycle over and over again, right? And again you will see at some point of time you'll get on the first state itself. So let me just, for illustration, let me tell you that these are cyclic. Okay, so this will again come out to be 1, and so here you will get 1 1 0 0. So you see, after the 7th clock cycle we're getting the same input as the first clock cycle, right? This will be a modulo 7, 1 2 3 4 5 6 7, because after 7 clock cycles you are there wherever it started, right? But we are interested only what's happening after the 5th clock edge, that is 0 0 0 1. So 0 0 0 1, that is our option B. That is the correct thing. So in this problem, what we first saw how the truth table of a D flip-flop looks like, which is the truncated form over here. And then what we simply saw was that we just noted down, we have to populate this truth table, right? So that means we have to populate the right side, the output side. To populate the output side, you need a truth table, which is here. But then you need inputs. How do you find inputs? You find outputs by seeing these wires. Okay, and that's how we solve this problem. There are different ways of seeing this. So what I'm seeing, that's a different approaches. So for instance, you can also say that d naught n is equal to q1 n minus 1. So there are different people approach the same problem in different manners. It's just a way of visualization. So I find easy to visualize like this. First row is completed, you copy the output in the next clocks for the next clock cycle, and then you obtain output. So my cycle goes like this. So if you see, it's we were here, then we came here to the input side, then we went to output side, like this. Different people have different approaches, so it's up to you how you find most comfortable. Okay, and that's how we saw this. That's how we solved this. Okay, let's move forward. There will be a few more problems related to this very similar principle. Okay, so now this question asks, what is the modulus number of counter of Q4, right? So this is the same problem as we had just done previous. So question 4 is what we have solved, right? We saw this. Okay, and this is the truth table that we had obtained, and we see that I am just going to write the output values over here. Okay, so we started with 1 1 0 0, then we got 1 1 0 0, then we got 1 1 0, then we got 1 1 1 1, and then 0 started creeping. So 0 1 1 1, 0 0 1 1, 0 0 0 1, 1 0 0 0, 1 1 0 0. Let's quickly convert them to decimal. So this will be 8 times 8 plus 4, 12. This will be 13. Sorry, 14. No, wait, 15. Just a second. 14. Sorry. This will be 14. This will be 15. This will be 7. Yeah. This will be 3. This will be 1. This will be 8. This will again be 12. So this is a counter, right? So how is it counting? It's counting 12, 14, 15, 7, 3, 1, 8, 12. Cycle repeats. So as I told you, the modulo means modulo. Another way of visualizing modulo is when after how many cycles we are coming back to the original number. So you see 1, 2, 3, 4, 5, 6, 7. After 7 clock pulses, we are coming to the original number, that is 12. So answer here would be 7. That means after 7 clock cycles, you'll reach where you started. This number differs. So here you can see 4 flip-flops. So maximum we could have gone from 0 to 15. Right? That's the maximum range we could go to. But here, sorry. But here we are stepping only on 7. Right? So that depends on the design of the circuit. Right? Here the application was this. Hence we got this. Okay. So that's a related problem that we could solve this because we populated the truth table. So this is the most important part. You first grab the depending on the original outputs, you populate the inputs, then output, then the next input, corresponding output, next input, corresponding output, next input, corresponding output, and so on until the values repeat. Okay, so that was question 4 and 5. Now let's go to question 6. Now before so just look at the diagram first. Okay, this is a BCD counter. So BCD is binary coded decimal. Okay, BCD stands for binary coded decimal. Means whatever the number is, you obtained its binary equivalent, and that's what it's counting. Why binary? Because as I told you, we require flip-flops which use which store the in 1-bit format, hence the binary codes. Okay, so it's a clock is given to it. This is, as we know, this requires some memory, and hence it's a sequential circuit. And the outputs, there are 4 outputs: D, C, B, and A, where D is the MSB, maximum significant bit, most significant bit, sorry. LSB stands for least significant bit. So this is, so essentially we are writing as D, C, B, and A. This is how we are expressing the whatever the binary number that's coming to us. Okay, now what we want, depending on the output, it says that we want to design decoding logic such that this is some logic that we want to design such that X is 1 for the D of this. D is nothing but the decimal value. So this is in binary. Correspondingly, there will be some decimal number. Decimal. We want to write that. Okay, I will see in the next truth table. So when decimal number is 2, 4, 5, and 6, we want output to be this output to be high. 0 for these values of D, and for 10 to 15, when the value of D is from 10 to 15, note D is this 4-bit number. DCBA in binary is D in decimal. This means the range of D can be from 0 to 15 because these are 4 bits, right? So D can be from 0 to 15. Hence you see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 to 15 is don't care. Again, don't care comes in this logic circuit. What is the minimal sum of products expression for X? In the last session also we saw what is the minimal sum of products, and we'll again use the same approach. In the last class we had used Karnaugh maps, right? Again we'll use the same thing. So just to explain the problem again, this counter is outputting some binary numbers, D, C, B, and A, 4 binary numbers, right? So it's a 4-bit binary number that's outputting, right? Corresponding to it, naturally there will be a decimal number, right? Whatever that decimal is, based on these values of D, C, B, A, we want some output X based on these, right? And we want to design this logic circuit so that we get such values of X. Okay. All right. So this is the circuit that has been given to us. Note that we are not interested in this part because we are already given the outputs, the DC, B, and A are being generated. BCD counter, we know how it works. Or in this problem, we don't even care how it works. We only are concerned about this logic circuit because we want to design this logic circuit. All right. So what do we know about this logic circuit? We know that this is the same thing that is returned to us. So you remember, for 10 to 15, we don't care. The value of X can be X, don't care. And the outputs are different here, right? Because 10 for 10 it will be different. It's not X here. Okay, I'm just denoting it like this. So the output is X here, and it was 1 for 2, 4, 5, and 6. This is from previous slide. See, X is 1 for 2, 4, 5, and 6. This. That's what I have done here. For 2, 4, 5, and 6, you see X is 1. Otherwise it's 0, and for 10 to 15 it's don't care. So I have just replicated the problem which was given in previous slide here. right? Now what I want to do, this is the truth table for this logic circuit, right? We want sum of products form. This is what we are required to find, right? So what I'll do, I'll draw Karnaugh map for this. Okay, let's draw a Karnaugh map. How do we draw the Karnaugh maps? We write all the inputs like this. So there are 4 inputs. It will be a 4x4 grid, 16 cells. AB here, CD here. So AB changes from 0, 0, 0, 1, 1, 1. Note that when jumping from one column to second column, only one of the inputs should change. So you see from first column to second column, A remains same but B changes. Similarly, from second to third column, A changes but B remains. B remains 1 here and 1 here. Similarly, from third to fourth column, A remains 1 but B changes from 1 to 0. And finally, this is a circular. So fourth column to first column, you see A changes from 1 to 0 while B remains the same. Similar logic is for rows. So CD denotes the rows. So here first row C is 0, D is 0. Second row C is 0, D is 1. You see C does not change but D changes from 0 to 1. Similarly, between second and third row, C changes from 0 to 1 but D remains 1. And you can, in the rest cases, you can figure out. Now what we'll try to do, we'll try to populate this K map using these values. So you see when D, C, A and B all are 0, X is 0. This means it's 0 here, right? When CD is 0 but BA is 0, 1. So when A is 1 and B is 0, like this, CD is 0, again we get a 0. Okay, CD is 0, 0 but BA is 1, 0. BA is 1, 0, we get a 1. So we get this BA. Note here it's BA, here it's AB, so be careful about that. 0, 0, 1, 1, this is 0. So we have populated the first row. Right, now let's do second row. When CD, okay, when CD is 1, 0, this means this row. C is 1, D is 0. We are now talking about this row. A and B are 0, so that is 1. This means this cell. This is complete. Now we are talking about 0, 1, 0, 1. So 1, 0, 1, 0. This is 1. This will be 1 because that's what we want. A is 1, B is 0, C is 1, D is 0. 1, 0, 1, 0. Alright, 6, 0, 1 and then 1, 0. So A is 0, B is 1. This means this cell. This is again 1. Right? 0, 1, 1, 1. This is given to be 0. This is this. This row is corresponding to this cell. For 8, we get D1, C0. D is 1, C is 0. This means this row. And then AB is 0. So this comes out to be 0. And then 1, 0, 1, 1, 0, 0, 1. So A is 1. A is 1 means this fellow. This is again coming out to be 0. And rest are don't care. Rest are don't care. Don't care we denote by an X. Alright. So now we have populated this. Now we want sum of products, right? And that too minimal sum of product. This means you want to form blocks of 1. Okay, blocks of 1, and you also include don't care. We want to make the largest blocks. That's our aim. So let's just try to find a block for this. So 1 and 0, zeros cannot be taken. X can be taken. So we cannot go here. We cannot go here, but we can come down and we can form this block, this rectangle. Correct? This is one way of doing it. Okay. Next, what I can do is this and this is remaining. Okay. Let's look at this now. We cannot go left. We cannot go down. This means we'll encounter a 0 here. So either what we can do is we can go up and we can go right. So let's go right. We'll counter 1 here. Okay. So first start from here and we'll go up, right? Like this. Okay. And we'll come from here. I'll use a different color. It will cause confusion otherwise. So purple rectangle was the one that we formed from where we included the ones. Remember, we just have to exclude 0 because we want sum of products form. Okay. Next, let's do green. So let's do here this thing. You see this block? There are no zeros included in this block. Right? We cannot go up because we'll hit 0. Similarly, we cannot go up here. But this green block will serve a purpose. Okay. Now let's try to find out. Let's try to write the expression for now. So X, the output X will be sum of the output X naught. Just a second. the output x, sum of products, right? This will be a sum of the purple colored one, let's call this x1, and the green colored one, sum of them, x2. Okay, this will be sum of them, right? Now we just need to find what is the value of x1. Okay, so let's do that. X1 means this column C and D we cannot take because they are changing. We only take the values which are constant. So you can see neither A is changing nor B is changing, right? So we write this value as A bar B. Why A bar B? Why did I put bar on A? Because the value of A is 0 here and we want 1. How to get 1 from 0? You negate that. And then it's multiplied by B. How do you get B? B is already 1, so I don't need to negate it. So I get A bar B for purple rectangle, right? But we also need to find what are the values for green rectangle. Okay, so let's just look at those values now. For green rectangle, you need to consider this row, these 2 rows, and these 3 columns, right? That's what we have to consider here. Okay, so yeah, let's try to figure out what do I get. So when you consider these 3 columns, A is changing because A is 0 and 1, so we cannot take A. Similarly, B is also changing, we cannot take B either. Okay, from this, just a second, let me see if I'm not doing anything wrong. Okay, yeah, I think green rectangle has to be restricted to here. Yeah. So green rectangle will be restricted to here. This we will already cover this, so we need not cover this again. It's no problem, but the calculation becomes easier. That's why I'm removing that. Okay. So now we see these in these two, from let's talk these two rows, right? These 2 rows, since D is changing, we cannot take D, but we can take C. C comes as it is because it's 1, and we are interested in how to make it 1. Okay, and in these 2 columns, right, A is changing, so we cannot take A, but we can take B. B is 0 throughout, but we want ones, not 0, so we'll take B bar. So the answer becomes A bar B plus B bar C. A bar B plus A bar B plus B bar C. So option B becomes the answer. Let me check. Yeah, 6 is B. Okay, so what essentially I was doing there is that, so in this problem we were given that this is a complicated circuit. It is a BCD sequential circuit followed by logic circuit. We were given that these are 1-bit outputs, D, C, B and A, right? And correspondingly we were given that we want to design this logic circuit such that this truth table is obtained. Once this truth table is obtained, we are required to find what is the expression for x in minimal sum of products form, right? That's why we did, based on this truth table. How did we populate this truth table? Because it was given in the problem itself, these things, x is 1 for these values and so on, right? Based on this we populated this truth table, and then we made the Karnaugh map, and then finally we said that for the purple and green rectangle, because we want only ones, and we can take x's to make our rectangles as big as possible. Okay, excuse me, we did that, and we finally figured out this is the expression that we cannot simplify this further. Note the term minimal here means you have to simplify this as much as possible. We cannot simplify this expression any further, hence this is the answer. Okay, so yeah, this is a good example that how sequential circuits involve the combinational logic as well as the sequential logic. So here you have some flip-flops, here you have some gates, so in this case NOT gate and AND gate, and again here. So this is a combination. This is how the circuits will actually look like real life, and this is a good example of that. Okay, right, so let's quickly move forward. We are running a bit short of time. So in this problem it says consider a 3-bit binary up counter. So we have seen this already, right? 3-bit means you have 3, Q2, Q1, Q0. Q2 is the MSB, hence we put Q2 first, right? And it's a 3-bit binary up counter. This means The first value will simply be up counter. So let's write the decimal value here. Okay, decimal value. Up counter means 0, 3 bit. So 2 to the power 3 minus 1. So maximum value can be 7, or you can also say it mod 8. Remember mod 8. So maximum value can be n minus 1, 8 minus 1, 7. It will run from 0, 1, 2 to 7, and correspondingly you can obtain from 0, 0, 0 to 1, 1, 1. This is how the truth table will look like. All right. From the counter output, so the question says this is nothing but your 3-bit up counter truth table. Okay, this question says that now we want to implement a logical function x equal to q2 times q1, right? If the frequency of clock is 8 kilohertz, now note that everything this is operating, there's a clock also running. Okay, everything this is happening at some clock. So this is clock pulse 0, clock pulse 1, clock pulse 2, finally clock pulse 8. After 8th clock pulse, it repeats itself. Okay, I can say 7th clock because we put 0, 1, 2, 3, 4, 5, 6, 7. Yeah, if this is 0, then at the 7th it will here, and at the 8th it will be 0, 0, 0 again, and the output will come out to be 0. Okay, as there are 8 clock cycles, right? The clock frequency is 8 kilohertz. So whatever clock is operating, it's operating at 8 kilohertz, which is the frequency of x waveform. So we are required to find the value of x. How does the x waveform look like? So let's do that. So again, as I told you, this is the truth table for 3-bit binary up counter. You see it's counting from 0, 0, 0 to 1, 1, 1, and it stops here, right? And then it starts repeating, and so I'm drawing this red line. You see that the value is again 0, 0, 0. So at 8th clock pulse, hence right. So now what we want to obtain, this is a logical function that we want to find the waveform for this, x equal to q2 times q1. So let's quickly do this. 0 times 0, 0, 0 times 0, 0, 0 times 1, 0, 0 times 1, 0, 1 times 0, 0, 1 times 0, 0 again, 1 times 1, 1, 1 times 1, 1, and then again 0 times 0, 0. Okay, let's plot this now. So there will be 8 clocks. I'm drawing, this is the clock that I'm drawing. This is clock. And now let's draw the output x. So again, assume that everything is happening on positive clock edge. Like, I mean, we don't know how it's implemented, but you can assume anything, positive edge, negative edge. Our answer will not differ. It will be consistent. But I am to keep things simple, or rather consistent, I'm considering only the positive clock edge without loss of generality. So this is the we have already talked about the positive clock edge, right? So at this positive clock edge only the outputs will change. So initially it's 0, right? Initially, because initially I'm assuming this is the starting point. So initially it will be 0. So this is the this is the first, second, third, fourth, fifth, sixth, 1, 2, 3, 4, yeah, 5, 6, 7, 8, and then it will come here again for 9th. Okay, so at first it's 0, second is also 0, it's 0 until 6th clock, 3, 4, 5, at 6th it rises. Okay, at 6th it rises. For 2 clocks it remains high, and then it falls, right? When it will rise again, it will again rise on. So this is 8th, 9, 10, 11, 12, 13, 14. So x will rise on 6th pulse. X rises on 6th pulse, and then 14th pulse, right? 8, and then you can see this is corresponding to 8, 9, 10. This is sequential, right? These things will repeat itself. 13, 14, 15. It will again rise on 6th, right? 6th and 14. So 14 minus 6, right, is nothing but the period is 8 pulses. I'm just interested in when the positive edge comes. So positive edge comes at 6th pulse and at 14th pulse, right? You can see this is the 6th edge, and that will come at 14th edge. So this means period of x is 14 minus 6, 8 pulses, 8 clock pulses, right? So we see that period of x is 8 clock pulses. Okay, so this means frequency of x would be 1 over 8 clock pulses. I can write it as 1 over 8 divided by 1 over clock pulse, which is nothing but 1 over 8 times clock frequency. Inverse of clock pulse is nothing but clock frequency, right? So this will be 1 by 8 times clock frequency is given to us at 8 kilohertz times 8 kilohertz. So answer is 1 kilohertz, option A. Okay, so it's very simple problem. We know the truth table for a 3-bit binary up counter, which is this, and then we just applied this logical operation x equal to q2 times q1. We obtained the waveform for that, and we saw it's rising at 6th, right? Positive edge 0 to 1 comes at 6th, and then again it will come at 14th, right? And then it will keep on repeating itself. So 6 to 14, this means 8 pulses is the difference. So 8 pulses is the difference. That means frequency is 1 over 8 clock pulses, and we simply obtain by putting the value of clock pulse. Answer is 1 kilohertz. Okay, very similar problem. This is the same problem as before. Again, we are given a 3-bit binary up counter, same as before. Q2 is MSB. Now the logical function is Q1 times Q0, and again we require to find the frequency of x waveform. So again, this is the truth table for a 3-bit binary up counter, and this is the this is the output function for which we are required to plot the waveform. I'll again quickly do this. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, and 0 times 0 is 0. Note that again after the 7th clock pulse we are repeating ourselves. So again what I'll do, I'll again draw the clock and x. This is clock and this is x. So let's draw. Again I'm interested only in the rising edge. Okay, so first, second, third, fourth, fifth, sixth, seventh, eighth. I think that should be sufficient. So again we are interested only in here. Okay, only on the rising edges. So let's draw them. Let's draw the reference lines quickly, and we'll draw the output waveforms. All right. So at the first clock edge, so initial value is 0. At the first clock pulse, it's 0. Only at the third one it rises. Okay. So this is after third one. So first, second, third. So it will remain 0, and it will rise here. Okay, and then it will fall at fourth, right? And then fifth, sixth, seventh it will rise again. Seventh it will rise again. It will fall. And then you can see that after 7, this is corresponding to 8. This is I told you this loops around 0 0 0, right? 9, 10, 11. So this is third, this is 7th. So again you see period of x. You can see either you can see from here 7 minus 3, right? And then next will come 11 minus 7, right? And then you can see 15 minus 11. All these values is nothing but 4 clock pulses. This is or you take either one of them. 7 minus 3, right? And then again after flow 4 clock pulses. That is after this first, second, third, fourth it will rise again, and then first, second, third, fourth. So you can see the period of x is 4 clock pulses. Period of x is 4 clock. This means x frequency will be equal to 1 over 4 of clock pulse. So 1 over 4 of, again we'll do the same, 1 over clock pulse. 1 over clock pulse is nothing but clock frequency. Clock frequency, which is 1 over 4 into 8 kilohertz, which is 2 kilohertz. So our option is B here. Very similar problem as to the one which we did before, right? Just that we need to see the truth table for the 3-bit binary up counter, and then we just simply plot the waveforms. Again, I'm taking the positive clock edge without any loss of generality. You can take anything, negative clock edge or this level, anything, the answer will remain the same. Okay, so that's that. Now for the next phase, this is a very consolidated problem now, comprising of I think 5 questions if I'm not mistaken. Yeah, so in this case, again, this is the same problem we saw like before. In this case, that case it was a D flip-flop. Here we have a JK flip-flop. So initial state, again, initial state is given as 0 0 0. What is the state after 3 clock pulses? So we'll just try to plot the truth tables for them again. So in this case, you can see this again, you see the JK flip-flop, but you see this circle here. I told you this is a negative edge triggered flip-flop. This circle denotes negative edge triggered, right? The truth table remains the same, except now the changes will happen at the falling clock edge rather than the rising clock edge. And you can see all of these 3 are fed the same clock. If all the flip-flops in the circuit are run on same clock, it's a synchronous circuit. All flip-flops have same input clock. This is a synchronous circuit, right? Okay, so now let's quickly jump into the problem. So this is the circuit given to us. Note that I have denoted it in such a manner. This is J0, J1 and J2, correspondingly outputs, and this is the inputs, right? And so we are required to find what happens after 3 clock pulses. So this means we are required to populate this truth table. These are the inputs, JKs, and these are the outputs, right? So how do we obtain the outputs? First of all, we know that initial state was 0 0 0. Okay, let's write the initial state as 0 0 0. Okay, and initially we don't care about whatever these values are, because this is a starting point. Okay, right, we require to see what happens after this. Now we require to find Q's over here. For that we need J's, right? Okay, so we need to find Q's. How do we find Q? Using the truth table. This is the same truth table as we saw before. This is the no change condition, this is the reset set condition, and this is the toggle condition when J and K both are, when both the inputs are 1, and this down denotes at the negative edge triggered flip-flop. Okay, so fine, we can obtain Q if we know J, but how do you know J2, K2, J1, K1, right? So first you look at the first flip-flop. This is the first flip-flop. Here J0, K0 is 1. This means this flip-flop is always in toggle mode. So that's a good observation that we can note, right? Secondly, we see that, so first we write J0, K0 is 1. Okay, fine. Secondly, we said that J1 and K1 is nothing but Q0 bar. See this? Okay, there's a mistake in the diagram here. This is not short circuit, this is crossing like this. Okay, be careful. Okay, J1, K1 is nothing but Q0 bar. Okay, so what's Q0? Q0 is 0, right? So J1, K1 will be nothing but Q0 bar. So this means 0 bar, which will turn out to be 1. This is also 0 bar, which will turn out to be 1, right? So again, as remember in the last problem also, we obtained these next inputs based on the previous outputs. So this is giving this and this. Okay, right? So now we just need to obtain J2 and K2. So J2 and K2, you see J2, K2, again this is not short. Okay, this is like this. Okay, so J2 and K2, if you see here, J2 and K2 are the same first of all, and they are coming from the output of this AND gate, and this AND gate is Q1 bar, second input is Q0 bar, Q0 bar times Q1 bar, hence this expression. Okay, so I'll write Q0 bar and Q1 bar. This means 0 bar times 0 bar, this will come out to be 1. This is the same as that, so 0 bar dot 0 bar, this will also turn out to be 1. Now once we have obtained the inputs, now we can write the output. Whenever the falling clock edge comes, these values, these input values will now give some result to the next output values. So we see J2, K2 is 1. This means this row output will toggle. So Q2, if the output was 0 before, it will now become 1. Similarly for Q1, J1, K1, we see this row, it will toggle again. So Q1 will become 0 bar. I'll write this like this, 0 bar. This will become 1. So this will also become 1. Similarly, this will become 1 because J0, K0 is also 0. this, and we see this always in toggle mode, right? So after first clock pulse, this will be the output, but we want after 3 clock pulses, so we will repeat this experiment, right? Let's again populate the input. So J0 K0 is 1, we can see. J1 K1 is nothing but Q0 bar. Q0 is 1, so okay, so 1 bar, this will come out to be 0. 1 bar, this will come out to be 0. And J2 K2 is Q0 bar dot Q1 bar. Q0 bar dot Q1 bar. This means 1 bar dot 1 bar. This will turn out to be 0. 1 bar dot 1 bar. This will also turn out to be 0. Okay. So what will be Q2, Q1 and Q0 now? Q2. Both the inputs are 0. This means first row. Output will be the same as the previous state. Previous state was what? 1. It will remain 1. What about Q1? We look at the J1, K1 inputs. Both are 0. First row. So Q1 will not change. 1. What about Q0? Q0 is J0, K0. J0, K0 both are 1. 1, 1. This means output will toggle. This will toggle from 1 to 0. Excuse me. Okay. Now let's complete the third row. First we'll populate the input. J0, K0 is 1. J1, K1 is nothing but Q0 bar. Q0 bar is 0. So 0 bar, this will turn out to be 1. 0 bar, this will again turn out to be 1. And Q0 bar times Q1 bar. Q0 times bar, so 0 bar dot 1 bar. This will turn out to be 0. 0 bar dot 1 bar. This will again turn out to be 0. So again, J2, K2 is 0. This means this row, the output will not change. So Q2 will remain as it is. But J1, K1 and 1, this means it will toggle this row. Toggle 1, it will become 0. We toggle 0 because this is also 1, it will become 1. So after 3 clock pulses, we get the output as 1, 0 and 1. Okay, after 3 clock pulses, we get the answer as 1, 0 and 1, which is option C. This is our answer. Okay. Right, now just to summarize this problem, we were given the initial state for this sequential circuit and we're required to find what happens after 3 clock pulses. First we see what is the nature of what flip-flops are used. So in this case we use JK flip-flops. So for that we saw the truth table for JK flip-flop, which is over here, negative edge triggered, which you saw like this. Okay, initial state we populated here. Now in order to populate the next state, we need the next stage inputs. How do we obtain the next stage inputs? We see this, right? We see that J0, K0 are 1 throughout. J1, K1 are nothing but Q0 bar. Okay, this is crossing over here also. These are not shorted, okay? Just to be very clear, these are not shorted. Okay, so and then we populate these inputs, we get the outputs. Then for the second clock pulse, again we populate the inputs based on these expressions. We get the output, and same goes for third row. And we repeat, and we get the answer as 1, 0, 1. Okay, so you can see that the value is changing 1, 1, 1, 1, 1, 0, 1, 0, 1. Let's see how far we go. Right, same problem, but now we are required to find the state after 5 clock pulses. Okay, the problem is the same. Alright, this is the circuit that we saw earlier. This is the truth table for that we had seen earlier. Now we are required to find up to 5 clock pulses. Okay, and the truth table, the JK flip-flop negative edge trigger, this is the truth table. And this is what we saw for the first flip-flop, both the inputs are 1. For second flip-flop, the inputs are tied to Q0 bar, which we see over here. And for the second JK flip-flop, the inputs are same, but they are the output of the NAND gate for Q1 bar and Q0 bar, which is the expression over here. Right, so we now again start populating this. But we know what I'm doing, I'm copying the answer from the previous, because till here we have already populated till third row. This is the same thing we have done in the previous slide, so you can just check that out. Okay, right, so now what we'll do, we'll now populate the fourth row. For fourth row we need the inputs. So J0 K0 is 1 again, right? J1 K1 is nothing but Q0 bar. Q0 is 1 here, right? So if Q0 is 1, so we say 1 bar equal to 0, again 1 bar equal to 0. Okay, 1 bar equal to 0. J2 K2 is Q0 bar into Q1 bar. So Q0 bar is 1 bar times Q1 bar is 0 bar. The 0 bar dot 1 will come out to be 0, and this is the same 0 bar dot 1 bar dot 0 bar will again turn out to be 0. Alright, so we'll do that again. So J2 K2 both are 0. This means this row, this means Q2 will be the same as the previous state. So Q2 will not change. Previous state was 1, final state will also be 1. Let's find out Q1. To find Q1, you look at the inputs J1 and K1. J1 K1 both are 0. This means this row, both are 0, the output will not change. So Q1 will remain same as the previous state. Q1 will remain same, this means 0 will remain 0. J0 K0 is 1 1, this is 1 1, this means the last row toggle mode. So the new output will be the inverted of the previous state. Previously it was 1, this means now it will become 1 bar, this will be 0. Okay, so now we get 1 0 0, but we need to find this row. Again we'll populate the inputs. So J0 K0 are both are 1. Okay, J1 and K1, so J1 and K1 are Q0 bar. Q0 is this, which is 0, so this is 0 bar, which is nothing but 1. Again 0 bar, it's nothing but 1. J2 K2, J2 K2 are nothing but Q0 bar times Q1 bar. Okay, Q0 is 0, Q1 is 0, so it's 0 bar dot 0 bar, which will turn out to be 1 because 1 dot 1. Again 0 bar dot 0 bar, which will again turn out to be 1. Alright, so now let's populate the output. So Q2 is the output for J2 and K2. The values are 1 and 1, 1 and 1, this means last row, this means toggle. So Q2 will toggle. Okay, Q2 must toggle. So Q2 was 1 before, now the new value would be toggling, 1 toggles to 0. Let's find Q1. Q1 is nothing but the output corresponding to the JK flip-flop 1 1. So JK 1 1, this is 1 and 1. 1 and 1 again means last row, this means Q1 should toggle. The new state will be the inversion of the previous state. So previous state was 0, the new state will be 0, the inversion of 0 is 1, so this will be 1. Finally J0 K0, this is again 1, again we see the last row. Again the Q0 input should toggle from 0 to 1. Okay, now thus we have obtained the output after the 5th clock pulse for this specific circuit, which is coming out to be 0 1 1. Okay, so it's coming out to be 0 1 1, which is our option D over here. So again, as we see, this is just an extension of the previous problem. There we solved up to 3, here we have solved up to 2 more pulses. Okay, but one more thing I should point out, we see that these values are not repeating yet. You see, we started from 0 0 0, we have not reached 0 0 0 yet. So this means the one cycle is not complete. We have not found the modulo of this problem, of this circuit yet. Alright, so whenever solving this problem, just try to keep an eye on that. If you are solving it correctly, you should reach the original value. Okay, that's always a good check to perform in these problems, in these which involve the counter circuits. Okay, right, so now this is the problem 10th, that's complete. Right, so so problem number 11 asks for that as what is the modulo number of the counter described in Q9. So for this circuit we need to find the modulo number, and note that the 4 options are 8 7 6 and 5. Okay, so what I'll try to, you know that we have already solved up to 5 clock pulses. This means, and 5 is not the answer, we know that because it's not repeating, so this is definitely not the answer. It's either 6 7 or 8. So what I'll try to do is, this is the same circuit as before, it's reproduced. So this time now we'll try to populate up to 8 clock pulses. Let's see if it's repeating in 6, we are good. If it's repeating in 7, we're fine. It cannot be more than 8 according to the problem, right? According to the options given in the problem rather. So let's just try to populate up to up to pulse 8, and let's see how the circuit, how the truth table looks like. Okay, and again this is the truth table for negative edge triggered JK flip flop. As you know, this symbol denotes negative triggered, which is denoted by this circle, negative, and this denotes edge. Okay, and these are the three how are the input values are connected to. So J0 K0 is 1, but J1 K1 is connected to this output Q0 bar, which is denoted like this. Similarly J2 K2 are same, and they are the output of an AND gate. The inputs are Q1 bar and Q0 bar, hence the expression comes out to be Q0 bar dot Q1 bar. And as before, we have since we have already solved up to pulse 5, right? So I have just populated this here. This is the same as you remember, it was coming out to 0 1 1. So I have reproduced the same thing up until here, and now we'll simply just go forward and try to solve for 6 7 and 8. So let's solve for 6. So the inputs are J0 K0 are 1 and 1. J1 K1 is Q0 bar, so Q0 is 1, so this will be 1 bar, this will be equal to 0, 1 bar, this will be equal to 0. J2 K2 is nothing but Q0 bar times Q1 bar, so 1 bar dot 1 bar, this will turn out to be 0. 1 bar dot 1 bar, this will turn out to be 0 again. Okay, let's find q2. Q2 we need to find j2 k2. J2 k2 has 0 and 0. 0 and 0 means first row. This means the next stage will be the same as previous stage. Okay, the value, so previous value is 0, next value will also be 0, no change. To find q1, we look at j1 k1 inputs, which are 0 and 0. Again, 0 and 0 corresponds to no change state, no change in state. This means q1 for the next state will be the same as previous state, which was 1. There is no change, 1 remains 1. To find q0, you require j0 k0. J0 k0 is in toggle mode, as we know. This means the output will toggle. So output was 1 earlier, this means now it will toggle to 0. So we obtain 0 1 0. We clearly see that we have not again reached the original state of 0 0 0. This means we must go on. Now to go on, again we need to populate the inputs. So j0 k0 is 1 1. J1 k1 is q0 bar. Q0 bar, q0 is 0. So 0 bar, which is equal to 1. 0 bar, which is equal to 1. J2 k2 is nothing but q0 bar times q1 bar. Q0 bar times q1 bar. So 0 bar dot 1 bar, this will turn out to be 0. 0 bar dot 1 bar, this is again turn out to be 0, because 1 dot 0 and here 1 dot 0. Okay, to find q2, you find j2 k2. J2 k2 as 0 0. 0 0 means first row. This means this value, the state will not change. So output state will not change. So output state was 0 earlier, next state will also be 0. Okay, let's find q1. To find q1, you look at j1 k1. J1 k1 and 1 and 1. So 1 and 1 means the last row. Last row means you must toggle. The next state will be the inversion of the previous state. So q1 must toggle. So we toggle 1. The inversion of 1 is 0. So it will turn out to be 0. To find q0, you require j0 k0. J0 k0 is again 1 1. 1 1 means last row. Last row means toggle. Output must toggle. So 0 must toggle. This means 0 must become 1. Okay. Again, we have not reached 0 0 0, which was our initial state. This means we must go one step further. This means we again must populate the inputs for clock pulse 8. J0 k0 are 1 and 1. J1 k1 are q0 bar. Q0 is 1. So it will turn out to be 1 bar. This means 0. 1 bar, again this means 0. This is q0. Sorry. J2 k2 is q0 bar dot q1 bar. This means 1 bar dot 0 bar. 1 bar dot 0 bar, this will turn out to be 0 again. 1 bar dot 0 bar, this will again turn out to be 0. Okay, let's populate the outputs. First q2 is the output for j2 k2, which are 0 0. 0 0 means first row, means the output will not change, so q2 must remain same. 0, it will remain 0. For q1, the inputs are j1 k1, which are 0. 0 0 inputs means first row. First row means again the output should not change, so q1 should not change. Initial input is 0, next input will also be 0. For q0, j0 k0. J0 k0 are 1 and 1. 1 and 1 means last row. Last row means q0 should toggle, the output should toggle. Output means q0 should toggle. Q0 is 1 initially, so final will be 0. Now you see we have reached the stage 0 0 0. This is the same state as the first clock pulse. Okay, at 0th clock pulse rather. So after traversing 1 2 3 4 5 6 7 8 clock pulses, we are there again, right? That's so this means after 8 clock pulses we are there, and hence this circuit is modulo 8, right? Why modulo 8? Because after you have to travel 8 steps, you have to wait for 8 clock pulses to reach there. Okay, so our alternate way of seeing is that there is another way of seeing it is like this. So this is the truth table. 0 0 0, this corresponds to 0, right? So I'll write this here: 0 0 0 1 1 1 1 1 0 1 0 1 1 0 0 0 1 1 0 1 0 0 0 1 and finally 0 0 0. What's the decimal? Sorry, this is 0 8 7 6, sorry, not 8, my bad. So what's the decimal, corresponding decimal? 0 7 6 5 4 3 2 1 0. Correct? That's what we saw. Highest number is 7 and it's counting down, right? And but a more truer way of doing it is seeing is when it's repeating. So it's repeating after 8 clock pulses, right? Okay, so hence the answer is 8, modulo 8. Okay, the next question asks if the initial state of counter is 0 0 0, which has been the case for this problem, right? What is its state after 28 clock pulses? Okay, so this is the problem. This is the truth table that we have obtained. Okay, now we are required to find what is the after 28 clock pulses, right? But we know after that, after 8 clock pulses, it's 0 0 0. So after 16, it will be again 0 0 0, correct? 24 will be 0 0 0, like this. So 25th would be 1 1 1, like this. This will correspond to 25th, 26th, 27th, 28th, right? 28th then will come out to be 1 0 0. Very straightforward. Again, how did we do this? We found out the modulo is 8. That the output repeats itself after every 8 clock pulses. So after 8 it will be 0 0 0. So after 16 it will be 0. 24 it will be 0. 25th will come here now, because this is 20 corresponding to 24 or 8 or 16. Right? So 25, 26, 27, 28. After 28 the output is 1 0 0. Hence our answer would be 1 0 0, which is option D. Let me check. Yeah, 12th is D, correct. So 1 0 0, again fairly simple. How did we find out? Because the modulo is 8. The modulo is 8 and we have already populated the truth table. There's nothing more to do for us, right? Just follow the truth table. You have all the 8 states that are there. You just need to figure out at which clock pulse you want to obtain the output, right? Which in this case happens to a 28 clock cycle. It is the similar to what the 4th clock pulse would be, which is 1 0 0. Okay. Now, moving forward is okay, yeah, this is interesting now. If the output Q2 of the counter described as Q9 as MSB, this means this we are describing as MSB, most significant bit. Q0 is LSB. How would you describe this counter? Okay, what are the options? 3-bit, all the options say 3-bit, which makes sense. There are 3 flip-flops, and as we had talked about, usually there is only 1 bit output bit per flip-flop. So 1, 2, 3. So that's why all the options is 3-bit. Binary, which makes sense because each output corresponds to 1 bit, hence binary, right? Okay, next thing is ripple or synchronous. Okay, this is a synchronous. Why? Because you look at the inputs of all the 3 flip-flops. Why synchronous? I've already talked about this. Synchronous, all flip-flops have same clock. First flip-flop, the second flip-flop and third flip-flop all have this same clock, you see this. Hence, this circuit is synchronous. Option A is wrong, option C is wrong. Next thing, is it up or down? For that we need to see the truth table. This was the diagram, this was the truth table. So now as you see, Q2 they are saying is the MSB, right? So 1 1 1, 1 1 0. So now you can just obtain the binary number corresponding to this. So we have seen that, right? So this will turn out to be 7 6 5 4 3 2 1 0, and as you can see, this is nothing but counting down. Clock pulse is increasing, but the decimal value is decreasing. This is referred to as counting down. Okay, so what we see is that this is a 3-bit because 3 flip-flops. It is binary. It is synchronous because all the 3 flip-flops have the same clock. It's a down counter. 3-bit binary synchronous down counter. 3-bit binary synchronous down counter. Option D. Option D. Okay. This was based just on the truth table that we have obtained for, I think, 11th problem or 10th problem. So there's nothing much that it's just in this problem we basically we had just looked at the definitions rather more than anything else. Okay, right. So problem 14. Now this is a different set of problems. The counter shown in the figure has 0 0 0 as one of its states, okay, as not initial state, as one of its states. What is the module number for this counter? So again, as you saw in this previous problem, we need to start somewhere, okay, but it says only one of the states, so we'll assume it to be the initial state itself. Without any loss of generality, will not be any problem. We'll assume it to be initial state. Okay, and again we solve this circuit, and again you see the options are 5, 6, 7 and 8. So maximum, if the question is correct and the options are correct, we need to go only up to maximum 8 clock pulses, but minimum of 5. So let's start. This is the problem, and this is the truth table that we need to populate. So just a second, sorry, 0 0 0 is initial state. Okay, this is the truth table. So you see this is this now why this is a flip-flop. All the 3 flip-flops, first of all, they're synchronous. You see all the 3 have the same clock. Okay, secondly, all the 3 are positive edge triggered. There is no circle here which is negative edge triggered, hence this is the truth table for them. Okay, and finally, finally we saw the initial state is 0 0 0. This we don't care, whatever it is. Now we need to go up to further clock pulses. For that we need the outputs. To find the outputs, we need the inputs. How do we get the inputs for next clock cycle? We look at this diagram. Okay, so first let's look at simply J and Ka. J and K both are 1. Previous problem like, so it's in toggle mode, right? JB and KB, you see JB and KB are same, right? But they are the output of XOR. This is a symbol for XOR, right? QA, QC and QA. So XOR of QA and QC. Okay, and you remember one of the properties of XOR is that it is high, the output is high only when one of the inputs are high. So if both the inputs are 0, the output is 0. If both the inputs are 1, the output is 0. Only when exactly one of the inputs is high in a 2-input XOR gate, the output will be high. You can see that truth table which we discussed in the, I think it's the second or third slide of this class itself. And in the previous session we also talked about. Finally, let's talk about JC. Okay, JC, you see, is the output of AND gate of QB and QA bar. That's QA bar and QB. This is JC. What is KC? KC is nothing but QB bar. Okay, so to populate the output for first row, we need to populate the inputs first. So JA and KA both are 1. Let's put them 1. JB and KB are QA plus KC, QA XOR KC, right? So 0 XOR 0 will be 0. Okay, 0 XOR 0, this will be 0. Again this will be 0 because this is the same. See that. JC is QA bar times QB. QA bar, this means 0 bar dot QB is 0. This will turn out to be 0. Right. KC is QB bar. QB is 0. 0 bar. This will turn out to be 1. We have the inputs. Now let's populate the outputs quickly. QC will be of JC and KC. So JC 0 1. This means second row. The output will be 0. So QC will be 0. To find QB, you look at JB KB. JB KB is 0 0 0 0. First row. The output should not change. The state should not change. It will retain the state. 0 will remain 0. Find QA, look at J and K. J and K both are 1. 1 1 means last row. The output should toggle. So QA should toggle. QA should toggle from 0 to 1. Completed the first row. Again, now we populate the inputs for second row. J and K remain 1. JB KB are QA XOR QC. QA XOR QC. 1 XOR 0. This will be 1 because one of the inputs are exactly one of the inputs is high. So 1 XOR 0 is 1. This will also be 1. So this is actually, these are equal. Okay. JC is QA bar times QB. QA bar, which is 1 bar dot QB. QB is 0. This will turn out to be 0. And that is QB bar. QB bar is 0 bar. So that will turn out to be 1. Okay, let's populate the output. QC will be output of JC and KC, which are 0 and 1. 0 and 1 means second row, means the output should be 0. So output will be 0. For QB, you look at JB, KB. The inputs are both 1. The inputs are both high. both high means last column, last row means output should toggle, means QB should toggle. This means it will come from 0, it will to 1. To find QA, you look at JK, both are high, both are 1, means last row means the output should toggle, this means QA should toggle from 1 to 0. Okay, we have not reached our initial state yet, so let's keep going. So JA and KN both are 1. JB, KB, QA XOR QC. QA XOR QC. 0 XOR 0. This will be 0 because both the inputs are low. So this will also be 0 because these are equal. JC is QA bar times QB. QA bar times QB means 0 bar dot 1. This will come out to be 1. 1 times 1. And QB is 1, so 1 bar, this will turn out to be 0. Let's populate the output. QC will be corresponding to JC and KC. JC, KC are 1 and 0. 1 and 0 means row 3. Row 3 means output should be 1. So QC should be 1. QB, look at JB, KB. Both are 0. Both are 0 means first row. First row means no change. Means QB should not change. QB should not change means 1 should remain to be 1. For QA, you look at JK. JK both are high. Both are high means last row. Last row means QA should toggle. QA should toggle from 0 to 1. Okay, we have still not reached 0, 0, 0 stage. Let's keep going. Populate the inputs. JK both should be 1. JB, KB should be QA XOR QC. QA XOR QC. So 1 XOR 1. Both the inputs are high, so the output in this case for XOR gate is 0. Exactly one input needs to be high, then only the output is high. So again 1 XOR 1, so this will also be 0. JC, KC, JC is QA bar times QB. QA bar times QB. 1 bar dot 1. This will turn out to be 0. KC is QB bar, QB is 1. This will again turn out to be 0. For QC, we need to look at JC, KC. JC, KC both are 0. Both are 0 means row 1. Row 1 means the output should not change, means QC should not change. So QC will remain from 1 to 1. For QB, you look at JB, KB. JB, KB are 0, 0. You look at the first row. First row means output should not change, means QB should not change, means QB will remain from 1 to 1. For QA, you look at JK. JK both are 1. Both are 1 means last row. Last row means QA should toggle. That means QA will toggle from 1 to 0. Okay, we have not still reached the 0, 0, 0 stage. Let's keep going. So JK both are 1. That will remain 1. JB, KB is QA XOR QC. QA XOR QC. This means 0 XOR 1. 0 XOR 1. Exactly one input is high, so the output will be high. This output will be high because these are the same. JC, QA bar times QB. 0 bar times 1. This will turn out to be 1 because 0 bar is 1. This is QB bar. QB is 1, so 1 bar. This will turn out to be 0. Let's populate QC. QC is nothing but output of JC, KC, which are 1, 0. 1, 0 means third row. Third row means output should become high. This means QC will become high, 1. QB, you look at JB, KB. JB, KB both are high. Both are high means we'll come to the last row. Last row means output should toggle. This means QB should toggle. QB will toggle from 1 to 0. For QA, you look at JK. JK both are high. Both are high means last row. Last row means the output should toggle. This means QA should toggle. So QA will toggle from 0 to 1. Have we reached? No, we still haven't reached. So 1, 0, 1. We still haven't reached 0, 0, 0. Let's keep going. The inputs are 1 and 1. JB, KB is QA XOR QC. QA XOR QC means 1 XOR 1. Both the inputs are high, so the output would be 0. XOR gate gives high when only exactly one input is high. Here both are high, so output will be 0. This means this will also be 0 because JB is equal to KB. But JC, QA bar times QB. QA bar times QB. 1 bar dot 0. This will turn out to be 0. KC is QB bar. QB bar is 0 bar, which will turn out to be 1. Let's populate QC. QC is JC, KC. Output of JC, KC flip flop. That is 0, 1. 0, 1 means second row. Second row means the output should be 0. The output should turn to 0, so the output will become 0 here. QB, to find QB, you look at JB, KB. JB, KB are both 0, 0. So 0, 0, this means the first row. First row means the output should not change. The output will retain as the previous value. So previous value of QB is 0. This means the new value also will not change and will remain to be 0. For QA, you look at JK. JK both are 1. 1 means fourth row. Fourth row means the output should toggle. This means QA should toggle. QA will toggle from 1 to 0. Now let's compare this row with the first row. Okay, So 0 0 0 and 0 0 0. This means we have reached the initial state. Okay, so what that would mean is that that the modulo for this is 6, because after 6 clock pulses we have reached the initial state. Okay, that's the definition. So for this, for question 14, the answer would be B, 6. It's a modulo 6 counter. I told you why it counts is that you can see, you convert this to decimal and you'll get some decimal number always. And modulo means when do you reach the original state. So original state we took at 0 0 0, and after 6 clock pulses we are reaching 0. Hence the modulo for this counter will be 0. Just to summarize again, so this was given to be one of the sequential circuit. We first of all see that this all the three flip-flops are JK flip-flops, positive S triggered JK flip-flops, and hence we see that we'll use this truth table. Secondly, we notice that these are synchronous, okay, because all the three flip-flops use the same clock. Alright, third thing we notice that in order to obtain, we also need to obtain the inputs, that are the value of inputs. So we see that the value of inputs JA and KA both are 1, which we see. JB and KB, they are the same, and they are the result of QC and QA. So QA and QC, and you XOR them. So QA XOR QC, right? Finally, JC you see is output of this AND gate, and the inputs are QB and QA bar. So QA bar times QB. Finally KC is nothing but QB bar. We see these inputs and we start from 0 0 0 as the output state, first state, right? Because it was given as it's one of these state, but we can simply assume it to be the starting state, the initial state. Okay, and then moving forward we first populate the inputs, right, based on these formula that we algebraic expressions that we have, and we obtain the corresponding output. So again we follow this trend. So we start from here, we go to the input side, we go to the output side, then we go to the input side, output side, input side, output side. So we follow this pattern and we keep on repeating the same exercise until we reach the initial state for 0 0 0, and we see that after 6 clock cycles we have reached the initial state of 0 0 0. Hence for this particular circuit we can see that this is a modulo 6 counter, because after 6 clock cycles we are reaching the initial state. Okay, so hence it's a modulo 6 counter. So that's a problem number 14. So problem number 15 says if the initial state of counter is described as 0 0 0. So notice the difference in tone. Here it says that it's one of its states, right, and we had assumed it to be the initial state, right? No, I'll go back. So this was an assumption, right? This is an assumption here. I told you, since this is one of the states, we'll again repeat, we'll get back to it at some point of time, right? Because let's say even if we assume the starting state to be 0 0 1, you see 7th cycle will be again 0 0 0 1. 0 0 1, sorry. So modulo will again come out to be 6. So when you want to find the modulo, it's irrelevant. It's just that you have to start at one of these states. That's it, and find the modulo. But if you want to find the exact state at the exact clock cycle, then you must know the starting point, and hence problem 15 explicitly says that the starting state is 0 0 0. Okay. Okay, just a second. All right, so initial state is, sorry, just a bit, I think one of these slides is missing. It's okay. So initial state is 0 0 0, right, and we want to find what is the state after, what is the state after 4 clock pulses. Okay, so let's just look at this diagram. So initial state is 0 0 0. We want to find what is the state after 4 clock pulses. So first, second, third and fourth. So after the 4th clock pulse the state is 1 1 0. So after 4th clock pulse the state is 1 1 0, which happens to be option A. So we just did not even need to, so option A is the same as previously. Yeah, so we do not need to even solve this problem, but just the key thing that to note, again I'll emphasize that here the starting state itself was given as 0 0 0. Let's assume the problem says that the starting state is 1 1 0. Okay, so let's create our own problem. So let's say if the question says, let's say question 16, state after 4 clock pulses if initial state is 101. Okay, initial state is 101 and we're required to find what happens after 4 clock cycles after this. So we need to look at the truth table. So 101 is here, right? So after 1 clock cycle it will become 000. 000 means this state, this and this are equivalent, right? Second this will become, third this will become, fourth will become 111. Then our answer would become 111. The truth table, it's not like that the algebra will change, it's just like that counting will change. So we start counting from here then, sorry, here. So 1, 2, 3 and 4. But in this case 00 was initial, required to fourth, so we count start from here. 1, 2, 3 and 4, and we find the answer is 110, which happens to be this. If this was the question 101, then the answer was 1, 2, 3, 4. Then the answer would be 111. This is just a hypothetical problem that we have discussed. All right, so we are out of time and we are also out of questions. So that is all for today. Just to summarize, today we had talked about sequential circuits. First we look at two of the very basic building blocks, that was the SR latch, and the second was JK flip-flop. And then we went on some more complicated problems like drawing the waveforms and finding the frequency of some known logical outputs. We also saw a question related to K-map, and in this question we saw that how do we still need to design combinational logic circuits even though we are talking about sequential circuits. It's not like combination circuit is now irrelevant. It is very much relevant, and it's a part of the design itself. Then the most of the time we have spent today on populating the truth table for these sequential circuits. That means different states. So QA, QB, QC, how do these values change? And first, for a given initial state, we first populate the inputs, find the corresponding outputs. Then again populate the inputs, find the corresponding outputs. Keep on repeating this exercise until we reach the initial state, right? Because these are counters, and they hopefully they'll repeat themselves, and the clock cycles after which they repeat the initial state, we reach the initial state, that is known as the modulo, which we have seen various examples of that. All right, so that is that from my side. That's a summary. If you have any questions or comments, please feel free to ask. Otherwise we'll close this session. All right, Gautam, any comments or questions?
No, sir.
Okay, then we'll close for today. Thank you for your time. See you next week.
Thank you, sir.